Our next experiment is calibration and testing of single phase energy meter. So here the aim is calibrate the given energy meter by direct testing. These are the operators we need for this experiment, and this is the circuit diagram for the experiment. Here we have a single phase variac and 1 voltmeter, 1 ammeter, and this one is 1 watt meter, and this one is not a watt meter, this one is a energy meter, and this one is load. So energy meter, in the sense already you know that energy meter. So previously in our home we are using that energy meter. Calculation of total energy per month, or otherwise it's mean a total time period we are calculating the total energy. So already this one is a energy meter. So in olden days we have this type of energy meters. Nowadays we have a digital energy meters. So from this we need to find out the how much of energy we are getting for each and every 25 revolutions. Why we are taking here only for 25 revolutions? In the sense, basically according to our requirement, for a 750 revolutions it will be a 1 unit. That meter will shows 1 unit. So that one is not possible. 750 revolutions, in the sense it will take a lot of time consuming. That's why we are taking only just for 25 revolutions. Here we are calculating only for 25 revolutions only. For 25 revolutions, how much time it will take and how much power will be consumed by the circuit. That one we are calculating here majorly. For each and every 2 amperes load, and how much time it will take for 25 revolutions. Suppose for example for 2 amperes load, how much time it will take for 25 revolutions, and then we can increase the load for 4 amperes. For 4 amperes for 4 amperes load, how much time it will take for 25 revolutions. It means the load is increasing continuously, the time period will be going to decrease. Okay, and this one is a theory for energy meter. And this is procedure actually. Precautions and theoretical calculation only for 25 revolutions. For a 750 revolution it will take a 1 unit only, so or otherwise 1 kilowatt hour. But for 750 revolutions it will take a lot of time. That's why we are taking only for 25 revolutions. And this one is a calculation energy meter reading even in the sense first energy meter calculation. So that energy meter we are calculating by using this formula 1000 into 60 into 60 by 30. So 1000 in the sense that one is for 1 unit. Here we are taking 1 unit, it means 1 kilowatt hour. Okay, that one for 750 revolutions. But here we are taking only for 25 revolutions only, you know. So that's why we are taking 25 by 750, in the sense 1 by 30 kilowatt hour. 1 by 30 kilowatt hour only we are calculating here. But why we are taking here 60 into 60, in the sense 60 into 60 is for seconds. So 60 minutes into 60 seconds. Then for 1 hour it will take a 3600 seconds. So that one we are calculating here. Then actual energy consumed by E2. So whatever the energy meter already I have shown now. So from that energy meter, what is the reading of watt meter reading, and how much time it will take for each and every 2 amperes load. Then finally we can find out the error value. So E1 is a constant for all the values, and E2 is continuously varying related to the load. So if load is increasing, E2 will be changing. That value we are taking into 100, in the sense, then we can get a error. So what is the error here, in the sense actual theoretical calculation, what is the value for 25 revolutions, and how much value we got by using E2 energy meter. So we are taking a value from subtract from E1 energy meter to E2 energy meter, in the sense we can get it error value. Okay, so this one is a tabular column for energy meter calculation. Okay, voltage. So initially what is the voltage? Here we are taking 220 volts for a single phase, and load current for each and every 2 amperes, and wattmeter reading, and time for 25 revolutions, and energy meter reading E1, and actual energy meter value, and as well as error value we can find out by using these formulas. Okay, this is the graph for final thing. Then we are going for experiment. First we are going to connect variac to ammeter, okay, variac first terminal to ammeter, and then ammeter second terminal connected for wattmeter M, ammeter second terminal connected for wattmeter M, and then here L is connected for energy meter C1. So here we need to talk about the energy meter C1 and C2 and P1 and P2. So this one also just like a energy meter. Here in energy meter we have a 4 pins. So this one is a C1 and the last one is a C2, and between P1 and P2 these two are short circuited internally. Okay, and these two are we are connecting for input side, and these two are we are connecting for output side. So for this energy meter we have 4 pins. One is a C1 and the last one is a C2, and middle one P1 and P2. So I am explaining here clearly. Listen, this is the actual energy meter. Okay, so this one having 4 terminals, C1 first one and C2 last one, and P1 P2 are middle terminals. These two are internally short circuited inside that meter, that's why we are taking P1 for input side and P2 for output side. It's mean this one is a common neutral point. So this one is a input side and this one is a output side. It's mean this one we are connecting at supply side, and this one we are connecting at load side. So those 4 pins only we can talk about here. Energy meter. This one is C1, this one is C2, P1, P2 middle. These two are connected internally short circuited, and these two we are connecting at supply side, and these two are we are connecting at load side. This one is a load single phase resistive load bank. Okay, and then we are going to connect for L to C1. So here this one is a L terminal, that one is connected for C1 of energy meter, and then next C2 is connected for load. So this one is a C2, blue color, so that one connected for load phase, and then P1 and P2 those two are internally connected, and P2 we are going to connect it for load end side, and P1 is connected for source side. So here P1 is connected for source side ground potential. Okay, if maybe you are going to connect this P1 for a supply neutral point also. So that neutral point already we have connected here for voltmeter, that's why I have connected P1 for this ground potential, and as well as P2 connected for load side. P2 is connected for, this one is a middle point, P2 is connected for load neutral point. Okay, and then we are connecting resistive load here. So totally circuit is completed here. 1 wattmeter, 1 ammeter, 1 voltmeter. We need to check it how much of voltage we are giving by using this variac, and variac is connected for ammeter, and ammeter to wattmeter, and wattmeter to energy meter, and energy meter to load. So this is the experiment. Then we need to turn on the power supply. Then we can increase. Here we have a different range of current values, load values. We can turn on this one, and each and every time we can using 2 amperes load. Okay, for each and every 2 amperes load we need to calculate, or we need to take the measuring values here. Okay, so here each and every button is 1 ampere load only. Okay, then I am going to turn on the power supply. Here turn on the power supply, and by using variac I am varying. You can observe the voltage value by in voltmeter up to 220 volts. Okay, by using variac I have varied 225 volts for a single phase. Okay, initially this energy meter disc is not rotating. Okay, simply in constant position. Then I am going to apply load here. First I am taking 2 amperes load. You can observe here in energy meter disc is rotating. Okay, so here red color will arrive. Once this one is red color, then it will come back again to here 1 revolution. Okay, 1 revolution. Like that 25 revolution we need to take. How much time it will take for 25 revolution, that one we are measuring by using the stopwatch. If you don't have any stopwatch, in the sense in your mobile also you need to check it how much time it will take for 25 revolution. Then we are increasing again 4 amperes load. Then here you can observe speed increases. I mean disc speed is increasing, revolution speed is increasing. That's why time period will be going to down. Then again I am going to increase one more load. Here this one is 2, this one is 2, this one is 2, totally 6 amperes. For 6 amperes you can observe here disc rotating very speed compared to 2 amperes and 4 amperes load. Then again I am increasing one more 2, it's mean 8. For 8 you can observe here revolution speed is more and more, increase again and again. Okay, like that you need to take it all the reading values in the tabular column. For this is the tabular column for energy meter. Here we have a different loads: 2 amperes, 4 amperes, 6 amperes, 8 amperes, 10 amperes, and these are the different values. These 2 values we calculated by using the formula. And this is wattmeter readings with multiplication factor 4 in that wattmeter. Okay, and these are the constant voltages, and according to load increases, load current increases, and little bit variations in voltage also. And these percentage error and these actual energy values we calculated by using formulas. So even for first load 2 amperes load we got E1 and E2 and percentage error, and for a second load 4 amperes E1 E2 and percentage error, and for 6 amperes E1 E2 and percentage error, and 8 amperes and E1 E2 and percentage error, and 10 amperes E1 E2 and percentage error. These are the values and calculations.